Here class, we're going to look at 9.5 notes, simple harmonic motion, damped motion, and combining waves. So the big things we're going to do here are building models for harmonic motion and analyzing it so we can come up with like what's the frequency, what's the amplitude, that kind of thing. But just know this is a very common application of a sine wave or sinusoid, a sine or a cosine model. So when we're talking about harmonic motion, we're talking about some type of a mass on a spring. And when we just hang the mass there, when it's just hanging there, it's at rest. And that's like the midline, right? And so when we compress it, the mass is closer to some starting point, some place where the spring is hanging than it is when it's at rest. Because when it's at rest, it's being pulled down. Gravity's pulling on it. And then when we let go, we pull it this way and let go, the spring comes down. It stretches as far as it can, and then it bounces back. And the idea is, if we measure time passing, and we compress that spring as much as we can, so we started off like up here, compressed, and then we just let go and it starts moving in that direction, and again, we're measuring as time is moving forward, we're going to see a sine wave or a cosine wave as time goes forward. The spring is being compressed all the way, it lets go, it gets to that rest position, and then it's stretched out all the way when it's at this time. And then it gets compressed back to that resting position, but then it gets compressed all the way again. And then time keeps passing. And it keeps looking like this as we go. So this is simple harmonic motion. This would assume that the spring will always return to these points A and C. Like it always gets compressed all the way to point A. It'll always be stretched all the way to point C. And so we always have that constant amplitude. So these are some assumptions that we make, that we have the acceleration of the object, the direction it's going to accelerate is in the opposite direction of displacement. So again, if I'm compressing it this way, that's its displacement d. I've compressed it. That means the acceleration is in the opposite direction of that and negatively proportional to it. Right? So the k is a constant. It's negative in this case because k is positive, so negative times a positive is a negative. And that just means it's in the opposite direction. So the acceleration is always going to be the opposite direction of the displacement. So there would be just simple harmonic motion with just that acceleration equals negative k times d. So there's no friction in terms of the spring bouncing back and forth, and thus there's no dampening of the amplitude. It's always that constant. We always go back to the same high point and the compressed position, and we send that same low point, the stretch position. They're always the same. So there are our equations for simple harmonic motion, and it just depends on how we want to model it. Do we want to model it based off of that maximum compression or stretching? If that's the case, we'll use cosine. Or maybe we have a model that begins from resting position and it gets knocked off of resting position, and if that's the case, then we'll use sine. Right? Frequency is something a little different. We've talked about the period of a sine wave, how long it takes to go from the midline up to the peak, down to the low point, and back to the midline. That was one period of the sine wave. But notice now we have the reciprocal of that. So omega, that's the thing that's multiplied by the t, the variable inside the sine or cosine. So that's what we were calling b in that section where we were doing sine and cosine graphs, and we found the period by dividing 2 pi by the absolute value of that b. So in this section, we're using the Greek letter omega, and we used omega some in that section as well. But we have the reciprocal here. We're flipping it over to come up with the frequency. All right, let's look at a scenario where we're going to do a model. So we start from the resting position. It says we are pulled a distance of 5 from its rest position. So we're starting down there at -5, and it takes 3 seconds for it to do one oscillation, meaning down from -5, once we let go up to +5, and back down to -5 where we started, takes 3 seconds. All right, can we come up with a model for that? Okay, again, assuming no friction. So we're going to always hit the 5s and the negative 5s. Well, because we're starting at our minimum, our negative 5, rather than the midline, we're going to use cosine to describe this motion. Anytime that we're started off of that midline, if we're started off of max and min, which is more realistic, we're going to pull the spring and let go, or compress the spring and let go. It makes more sense to use a cosine function for a lot of these. Alright, the amplitude is the 5s that we're going up and down to, so we're going to have a 5 times cosine. Because the period is 3 pi, we can take 2 pi divided by w to get that 3, so that means omega, or w, is 2 pi over 3. So our model would be, in this case, negative 5 cosine 2 pi over 3 times t. Okay, negative again because cosine typically starts at its max and goes down for one period, but this is starting at its minimum and rising and coming back down. So that's why we have that negative. Alright, so this is kind of reversing the process when we're talking about analyzing the harmonic motion. We're reversing the process and giving you the equation instead of you coming up with it, and you describe the motion. So when t equals 0 here, because we're on the sine function, we're on the midline, and then we rise, fall, rise for one period. Alright, so we're going to start from resting position and begin compressing the spring. Alright, the maximum displacement is given by the amplitude, and then the time required for one oscillation, that'll be the period. So 2 pi divided by the number in front of t, so that's going to be pi seconds. Alright, the frequency would be 1 over pi. It's the reciprocal of the period. Alright, when we're talking damped motion, now this is more realistic. So when we compress that mass and let go of it, it'll bounce that far the first time. There's its rest position. Well, it won't get back to where we compressed it initially. So if this was like the compressed the spring was the first time, and it stretches out this far and it comes back, it's not going to compress all the way again. And then when it gets done compressing and it comes back down again, it's not going to come down as far as it did. So we're still having like a sine wave as time goes on. But the thing is this sine wave is what we call damped. It gets smaller and smaller and smaller. So basically, if you think about, if you connect the dots at the max or the min, they're getting tighter. They're getting closer and closer and closer together. And that's what we mean by damped harmonic motion. Alright, so here is what that looks like. You can still see we've got some of the guys that we had there before. We still have the cosine or the sine. We have A, that kind of amplitude, that maximum amplitude. There's omega that we saw before, but now we have an exponential. And in particular, an exponential with a negative value being multiplied by the time component. So if you recall, e to the negative t kind of looks like this. And so what this is doing, it's multiplying our amplitude by something that's falling towards 0 like this. And that's keeping that, if I mirror image it on the x-axis, that's basically keeping that sine wave inside this little, it's making its maximum and minimum be squeezed in between this curve that won't allow it to continue to get back to where it was before. So that e to that negative power is going to dampen these oscillations and make them less and less and less as time goes on, which again is much more realistic. And this slide is going to show us the reason why we have the e to the negative t here and the e to the negative t here, and that sine or cosine wave live in between those two. When we consider that this function, this e to the negative t over pi times the cosine, because we know cosine is bound between positive 1 and negative 1, that means in absolute value it's always going to be less than 1, or less than or equal to 1. So we know that the displacement of the mass on the spring is always equal to that, because that's the displacement function. Now again, it can be positive or negative because of the cosine, so that's why we have in the absolute values. And because it's in absolute values and I'm multiplying, one of the properties of absolute values, I can multiply, or take the absolute value of each thing that's being multiplied inside that product. And then we know the absolute value of cosine is less than 1. So that means that this thing, which is being multiplied by something that's less than or equal to 1, at most this thing will be equal when we multiply by cosine, will be equal to this, but it could be less than that. So what we mean by that is, because this is at most 1, and I'm multiplying this times something that's as big as possibly it could be is 1, then we know that that product will be at most what's in the green. Because when you multiply by something by like 0.9, it's less than what you started with. When you multiply by 0.2, it's less than what you started with. And since this value, the absolute value of cosine, can be at most 1, then that product can be at most what we have in the green box there, which is the absolute value of the negative t over pi. All right, the absolute value of negative t, absolute value of e to the negative t over pi. E can never be negative. E to a power, I should say, can never be negative as long as we're dealing with real numbers. So what we end up with is this thing in absolute value is equal to this, or technically less than or equal to this. So that means it's bounded above by the positive version and below by the negative version. That's just the definition of absolute value. And so that means we get an e to a negative t power above the axis and below, which bounds that cosine wave and kind of sends it to the x-axis. So there's what I'm showing you is the blue curve is the e to the negative t over pi times the cosine. That's our damped trigonometric curve. The pink curves are the e to the negative t and negative e to the negative t. Those are the ones that are sending this e to the negative t over pi cosine down to the x-axis. So again, as this goes on, if we were to keep going forever and ever and ever with this, it would just continue to get tighter and tighter and tighter until you could basically not tell the difference between the x-axis and that dampened cosine function. It would just barely be above the curve at all and below the curve as time went off. So that's what we mean by damp. We're taking that cosine function and we're squeezing it down to the x-axis as time goes on. Right, notice the peaks and the valleys are still taking place, the same place they took before. If that dampening function wasn't there, again the dampening function being the e, if that wasn't there, we just had the cosine. The maxes and the mins, the zeros, the lowest points and the highest points, they're still taking place at those same places. All right, as you read through these last objective, the sum of two functions, one of them being a trig function, one of them being some other algebraic function, typically a line, possibly two trig functions. I encourage you to use your TI calculator for this, or some type of graphing calculator for this. So here's our x over 2 plus 2 sine x function, and I'm just going to go to zoom and pick option zoom trig. And again, what this does, we'll place tick marks at like pi over 2, pi, 3 pi over 2, like on the unit circle on all the 90-degree angles when you're in zoom trig. You can control that again with your window. I personally like to have, instead of being pi over 2, I like it to be pi over 6. And now when I go to graph, I get these little tick marks every pi over 6 units. So that's pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, pi, so on and so on. But you can see now that this graph is rising as we go left to right. That's the x over 2 part. If I put y equals, just so you can see it, just that part by itself, that's going right through these kind of midline intercepts along the way. So normally I would, like with the sine function, I would go up, I'd come back down, I'd go back up again, and anytime I would hit the midline, I would be at multiples of pi. So like 0, pi, 2 pi. And if I put in pi, you can see I'm right at that midline intercept right there at x over 2 sine x. So again, it's that line is where we're starting the sine from. Basically, you can think of it as we're starting with this line and then we're adding the sine function up and down to this line. So it's like that sine wave kind of gets sent up along this slanted line rather than along the x-axis. All right, here is a sum of sine and cosine, 2x. So I'm going to do that in my calculator. All right, again, zoom trig. I'm doing the zoom 7 zoom trig. And there's what I get. That is the red curve right here. Right, and you can see what's happening is when sine and cosine, because it's cosine 2x, it's not just regular cosine, but when they kind of both hit at a maximum or a minimum, the graphs get kind of boosted down, like doubled up right there. But when they are opposites, like at pi over 2, the cosine 2x function is opposite the sine x function. And so when we add them together, we get 0. And so we're hitting the x-axis at those places. But again, your calculator can do all of this. Your calculator can even do the others. It's just when you want to graph them all on the same axis, it's going to look really messy unless you come over here to the side and select some other type of graphing icon. Now, some of the newer ones with the LCD screens, they can do color. But if they don't have color, you'll have to come over here and start hitting enter. So there you can get a bolded version of the line. Hit enter a couple times. That's shading above and below. And there's a dashed version of the line. So you can do that so you can kind of distinguish the graphs. So there's the sine function in bold. And then here comes the cosine 2x function. And it's not dotted. Let me select. There you go. That's the one that's dotted. So let me graph it again. So there's the sum of the two. Right, there's just the sine. Right, and then there's the dashed one. That is the cosine 2x. So there are ways to get, even with the black and white one, kind of distinguish them. It's still not as great as having color.